Today we're going to talk about how to find the pH of a strong acid solution as opposed to the pH of a weak acid solution. We have to approach the two very, very differently. All right, so if we start with this question, what is the pH of 1 molar HCl? Okay, HCl is a strong acid, right? We've got 7 strong acids that you have memorized. And what makes a strong acid, why we classify it as being a strong acid, is because it's a strong electrolyte. So what does that mean, it's a strong electrolyte? Well, that means that it completely dissociates in water. So, 1 molar HCl. So, hydrochloric acid in solution is going to be H plus and this is a one-way arrow in solution. It only dissociates. We never get the reverse reaction going on here, ever. Hydrogen, which is really what? Hydronium. And chloride ions in water, and that's all. Complete dissociation. Never the reverse reaction. So what we're going to do now is we're going to go through a series of steps that we're going to use with all of the acid-base equilibrium problems that we do. For this particular case, it's going to seem kind of silly, but I need you to begin thinking about approaching acid-base problems in a very methodical way. All right, so the question I want you to always ask yourself is, what are the major species in solution? We're going to lose this. Always, I want you to ask this question. And so, what do we have in a beaker of 1 molar HCl? Let's make it turquoise. Well, we have water. Okay, got that. What else do we have in there? We have hydrogen ion. We know it's hydronium. Hydrogen ion. We have chloride ion. Do we have any HCl associated? No. Completely dissociated. 1, 2, 3 components in this solution: water, hydrogen ion, chloride ion. All right, now whenever we are doing pH problems, okay, we are looking for how much hydrogen, hydronium, how much hydrogen ion is in solution, because that's what pH is, right? The negative log of the hydrogen ion concentration. And so we've got the hydrogen that's coming from the HCl, But where else do we have hydrogen coming from? The auto-ionization of water. And so we have to think about that as well. So we must take into account the auto-ionization of water. That being water going to H plus OH minus. Okay, but at room temperature, what is the concentration of hydrogen ion coming from the auto-ionization of water? Well, 1.0 times 10 to the minus 7th is very, very little compared to the amount of hydrogen that is coming from this 1 molar HCl. And not only that, but the hydrogen that is coming from the dissociated HCl, what's it going to do to this auto-ionization equilibrium with all this hydrogen added from there? It's going to drive this reaction left. And so that means that the concentration of hydrogen ion coming from the auto-ionization of water is going to be even less than 1.0 times 10 to the minus 7th molar. And so we don't need to worry about it, okay? It is not going to be a significant enough amount of hydrogen ion to have to take into account to calculate this pH. All right, so I'm going to write that down actually. What I just said. But exactly like I wrote it here. The H plus from HCl will drive the auto-ionization reaction to the left. So it will be less than 1.0 times 10 to the minus 7th molar. Okay, so the hydrogen ion that arises from the auto-ionization from water, you know, usually just in a glass of water is 1.0 times 10 to the minus 7th molar. But because the hydrogen ion from the hydrochloric acid will drive that auto-ionization reaction to the left, it's even going to be less than 1.0 times 10 to the minus 7th molar, the hydrogen from the auto-ionization of water. So this is significantly less. This is significantly less than 1.0 molar H plus. So we call it negligible. So we call it negligible. It is so very, very important as we are doing pH problems that we have a very clear understanding of where all of the hydrogen ion is coming from. The hydronium ion. The hydrogen ion is coming from. We have to take inventory of where it's coming from and decide whether or not this source is a significant source of hydrogen ion. Okay. So in this case, we're working with 1 molar HCl. Okay, much greater concentration, 1.0 molar hydrogen compared to this. And so we can say, we don't need to worry about the hydrogen that's coming from the autoionization of water. This is the hydrogen ion that is affecting the pH, that's dictating the pH level. And so then it's very simple calculation. The pH is equal to the negative log of 1.0. And that's equal to 0. Okay. So really in the end, you guys, what did we do? We just found the negative log of strong acid concentration, and that gave us the pH. But all of this was a process that you need to think about, because tomorrow night it is the pH of a weak acid solution, and things get a bit more complicated. And then we move into the pH of a weak base, and they're even more confounding. And then finally we have to do the pH of a salt solution, and it's going to make your mind spin. And so it's important that we understand a process, that we have a process in place to start thinking about what do we have in solution, what is a significant source of hydrogen ion, what's not a significant source of hydrogen ion, so that we know what we're going to use to find that pH. All right, that's all.